Last week I showed off the beginning of a Ben Eater style VGA card that I was building. And in order to save on part count, I'm using the 74440 counter, which is a 12-bit counter, instead of the 74161 counter that Ben uses, which is a 4-bit counter, and of course then requires 4 chips in order to get the 10 bits that are required. Well, 9 or 10 bits depending on whether you're talking about the horizontal sync or the vertical sync. One of my viewers of my video was concerned because the 7444040 chip is a ripple counter, and the 74161 that Ben uses is a synchronous counter. And so I want to look into that. First, I want to talk a little bit about the difference between these two counters. So first, let's take a look at the data sheet for the 74161. The 74161 is what's called a synchronous counter, which means that all the outputs change simultaneously. Here's how that's achieved. What happens is there's a clock signal that's sent in, and it goes into the clock of these D-type flip-flops, each and all of them. So they're all clocked. And without any special gating, these would all just count at the same time. So they would all go 10, 10, 10 at the same time. But this is the clever thing about these synchronous counters. What they do is they feed back the signal from the output of one, not into the clock input of the next one, but into a gate that only allows the gate, which basically turns it on or off, or determines whether the D-type flip-flop is going to actually accept the clock signal. So this is turned off unless the output of this is bit 1 or bit 0. The output of bit 0 has to be a 1 in order for the output of bit 1 to be able to receive the clock signal. So that means this one will only clock every other time, only when this one is turned on. In the next stage, you can see that there is an AND gate that has 3 inputs. So it has, one of the inputs is just the enable pin. The other input is from the prior 2 bits. So both of these have to be high in order for this to be high, in order for that to allow this clock signal to be accepted. And so this one will only change when a clock signal occurs when both of these are high. And then likewise, this one has a 3-input AND gate and plus another AND gate, so that's equivalent of a 4-input AND gate. And so only when all 3 of these are high will it allow the gating to turn high, and then it will allow for the clock signal to be accepted. And so in that way, it guarantees that each of these each of these bits will change all at the same time on the clock pulse. And in a clever move, they do the same thing with this called RCO. This is the ripple count output. And so this gets forwarded to one of the enable pins of the next chip, and it makes sure that the next chip behaves in the same way. So this, if you look at this, you can see that when this is low, which means these outputs are high, this is an inverter. So when these are low, it goes into this well, this is kind of a rewritten NOR gate. But anyway, you can see that when the way this is written is an AND, but these outputs are negative. So when these are negative, all negative, meaning when all these 3 outputs are all high, then this will go high. And likewise, this one is connected directly. I don't know why this one's connected differently, but this one's connected directly to this AND gate. And so when all 4 of these are high, then the ripple count output goes high. And because this is connected then to the enable chip that says when these are all high, enable the next clock cycle to be read by the next chip. And so the next chip in the sequence, when its clock chip goes connected or goes high, then its counter will also count. But that can only happen when all of these. So the next chip can only count when all of these are high, which is exactly what you'd want for a counter. And that's why you may have wondered, like, why does Ben connect all the clock signals together on those on each of the three 74161 chips that he installs, and that's why, because that's how these are designed. Now let's take a look instead at the ripple counter or asynchronous counter. This is the SN 744040 4040 chip. And here you can see how these are connected. These are what are called toggle flip-flops. A toggle flip-flop is basically a JK flip-flop with the J and K inputs tied together. And then the clock input simply toggles it back and forth. So these are toggle flip-flops. And so each time a clock happens, it toggles it. And then you can see that when the output of this, these toggle, by the way, you can see it's got a inverting buffer here. So when the clock cycle goes negative, then this will switch, this will toggle. So when this goes negative, then this output here is positive. So when this is actually a 0, then this output becomes a 1. But more importantly, because that output is negated, when it triggers the next one. So this will go, when the clock pulse goes low, if this was initially low, it'll go high, which will cause this output to go high. Then when the clock switches again up, then this will go, then this output will not switch, so nothing will happen. When this goes low again, then this output switches to low, which looks like a low transition to this one and causes the next one to count. And in this way, each one counts. This will count half as often as this one half as often as this one, and so forth, all the way through all 12 bits. Now, the downside, the plus side of this circuit is that it's very simple, and it doesn't require a lot of gating, and so it's very easy on a 16-pin package to put this 12 output, 12 pin or 12-bit ripple counter. So that means that this can all fit in one small package. But the problem with it is that there is a delay, because you can see that as this output goes through an inverter, and then it goes through this clock input, and you can see there's an inverter there, and then of course there's circuitry within the toggle itself, and so each of these has a delay, and that delay is passed forward from bit to bit to bit. And so that means that when this bit, if these bits, for example, are all 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then the whole thing counts to the next, flips to the next bit, then this goes 0, makes this goes 0, this goes 0, 0, 0, 0, 0, 0, 0, 0, 0, flipping this one to a 1, and you can see that could introduce quite a bit of delay. So let's take a look and see if we can figure out how much delay it does. So here I've just wired up this chip to a bunch of LEDs, and this is the low order bit, and it works its way to the high order bit, and that's all wired up to this. And so if we take our Ben Eater clock circuit and we connect the power to it, and we connect up the clock, and here I have wired this to the reset, which is, and this chip is a positive, not a negative reset like the clear pin on the 74161. So if I hook this up and I clear it, there you can see it's cleared. And now if I were to step this clock, we can see that it is not working. There we go. So you can see as I step this, it goes forward and it counts in a binary fashion as you'd expect. And just to make sure it goes all the way through, let's switch to the clock circuit and turn it up so we can see the action on the higher order bits. So you can see this is counting, this is working as we expect. as a binary counter. That's all I wanted to show here. So now I want to check the timing, but this is going to be hard to do with a slow clock like the Van Meter clock. So instead, I am going to hook up a clock circuit. This is just a 7-4 HC, we could use an LS, 74HC04, which is the hex inverter that we're so fond of. Here I'm taking a pair of 1,000 ohm, 1 kilo ohm resistors, and I'm hooking it up hooking them up between the input and output of adjacent NOT gates. And here I am connecting the output of one to the input of the other. And here I am putting a 10 megahertz crystal across the input of the first one to the output of the second one. And this just creates a nice little oscillator circuit. It works pretty well. So let me hook the power up to this. And I don't know why we're not getting all the lights going on. We'd expect them all to be lit when we're clocking at such a high speed. Oh, I haven't connected the clock yet, that's why. That's just stray bits. Let's connect the clock output to the clock input there. And there you can see all the LEDs they appear to be lit constantly, but of course that's because this is at 10 megahertz, this is at 10 megahertz, or sorry, yeah, 10 megahertz. This one's running at 5 megahertz, really half the speed of the clock. This one's blinking at 5 megahertz divided by 2 to the 12th or 4096, which is still very, very fast, way too fast for your eye to see it or for the video to pick it up. So let's switch to an oscilloscope. So let me pull all of these out. Just going to get, LEDs are not going to be helping us anymore. So instead, let's take our oscilloscope input and let's put this input at Q1 or Q0, which is that pin. And then the next output, the other probe, will connect way up here. That is the highest order bit, Q11. And then connect the power. Switch to our oscilloscope. Now let's take a look at what we've got going on here. So let's put this in normal mode, and let's take a look at the signal that we're getting. Here I've got this set at 100 nanoseconds, and you can see, the clock is a little bit wobbly. But if we let's change this to single shot mode, we can take a look here and we can see what we've got. So we would expect when the output of Q0 goes low, then the next one would go high. But it's a little hard here to see just because the signal isn't super clean. So I'm going to move this from Q0 to Q1, Q2. So this will be a little bit cleaner signal, I believe. So let's go back to normal mode. And then switch to single shot. And there we can see it again. Actually, this looks pretty good. So the oscilloscope is sort of helpful, but what would be really nice to see would be a bunch of delays as they're shuffled through the chip. So I am using here a Hancock 6022BL. You can get this in for about $65. Let me show it to you. So it's a Handtech. It's a 6022BL. This for about $60 you get the 6022BE, which is a 2-input oscilloscope that hooks up to your computer through a USB port. For another $20 on top of that, you can buy one that has an 8-input logic circuit. So let me hook this up. I'm going to stop the video and get this hooked up, and then let's take a look at what we can see from the logic analyzer. Okay, so I have the logic analyzer hooked up, and I'm running a program called PulseView. And what we're going to do is we're going to take some samples. So let's run at 48 megahertz. That's the fastest that this can do, which fortunately should be fast enough for a 10 megahertz clock. Let's take 50 million samples, and let's run. All right, so taking a look at this, we can see that we're counting here. Well, we can see that one of my wires came loose. This one here popped out. Also, I only have 8 channels, so I'm not connecting obviously all 12 channels. To get a cleaner signal, I'm just using the top channels, but this will give us an idea. Whatever this delay is that we get from this ripple counter should be, we simply like multiply that by 1.5, and that should tell us what the total delay would be. This should give us a pretty good idea, though, if we think this is going to work. So let me run this again to get some fresh samples. And D2 is still behaving strangely. Oh, I see the problem there. Let me try this again. All right. I'm going to stop the video a second and find out what's going on. All right, all connections seem to be good now. We're going to do another run. There we go. So now you can see that we have the clock signal here, and well, actually, this is going to be the 4th bit, and then here is the next bit, and so on. And you can see that each one steps, you know, in tune with the one above it, and one above it. But what we want to do then is get enough samples here so that we can look at here where it transitions. What we're really interested in is this delay here when it transitions, when all the upper bits, all 7 of the upper bits are high, and they transition to low. That's going to be the longest delay. So let's zoom in right there if we can. So zooming in. Keep zooming in. So we're going to try and find what this delay is. Still really can't see it. So we have a long way we can zoom yet. There we go. Now we can actually see the individual, these dots represent the individual measurements. And you can start to see that there is a bit of a delay. And we can see that I'm in the wrong place. That's not the one we want. Over here is. Right there. Okay, now we can, that's touchy. Now we can measure this using the markers. So let's set this marker at the beginning, this transition. Come on, marker. And then we'll set the other marker at this transition. And then we look here, and that tells us that the delay is, zoom in one more time. There we go. So the delay is about 42 nanoseconds, which means the total delay will be about 64 nanoseconds. Now, the clock is running at 10 megahertz. So the clock signal is about 100 nanoseconds, or exactly 100 nanoseconds. And so this is the total ripple delay we're going to have here is 64, which is more than half the clock cycle. So potentially that could be a problem. But if you remember, the signals that are really important are the horizontal sync and the vertical sync. And those signals are driven by the counter and by the AND gates, the logic that is set up by the logic gates that do the counting. So let me get this stuff out of the way here and remind you what that circuit looks like. Let me zoom in on that. So if you remember, we're looking for a 200, 210, 242, 264. And as it turns out, none of those require the bottommost bit. They only require the second bit. So that reduces the delay. But that increases the effective cycle length, if you will, from 10 megahertz down to 5 megahertz, or from 100 nanoseconds to 200 nanoseconds. And 64 nanoseconds is less than half a clock cycle at that rate. So I think we're still going to be good. As you can see, I have my board pretty well produced, and I am about ready to hook it up and test it. And I will show you that on my next video. Thank you very much for watching. I appreciate your support. If you liked what you see, please subscribe. And if you want to be alerted when I create a new video, which is usually Sunday morning, you can click the bell. Thank you very much.